We now turn to the use of the cosmic microwave background as a cosmological tool. This turns out to be the most powerful tool in our arsenal today, and it's what really led us into the era of precision cosmology. The basic idea is as follows. If we had something sufficiently large in the early universe that can be measured, and we knew what redshift it was, then we could apply angular diameter test to it and constrain cosmological parameters from that. And the largest possible thing we could think of would be the particle horizon at the time, which is the distance out to which causal connection can be established at the time that the universe was that old. If we can infer the size of the particle horizon from physical reasons, and if we can somehow find its signature in a microwave background, then we can perform the test. There will be density fluctuations in the early universe, and those are left over from the quantum fluctuations from even earlier times in the history of the universe. And they would manifest themselves as slight variations in density. You can decompose those in a series of waves overlapping, and the matter would fall towards the densest spots, and because the matter and radiation are tightly coupled before the microwave background was released, radiation would follow, inducing some slight Doppler shifts in its thermal emission. So when microwave background is released, the decoupling stops, and whatever pattern of fluctuation was there will remain frozen and observable today. Theory predicts that those who have amplitudes of some parts in million of the present day temperature, which is 2.7 degree Kelvin, and so be very, very subtle effect to measure. So for a long time, cosmologists tried to measure these fluctuations, and finally they succeeded. There have been many experiments leading towards this, but the first really successful one was a balloon-borne microwave background measurement from Antarctica called Boomerang. It was led by Andrew Lang and Paolo De Bernardis, and they were the first ones to have convincing measurement of these fluctuations at the scales that are relevant here, and the first ones to actually infer cosmological parameters from that. This was probably the single most important measurement at the time, at about the same time as the supernovae yielded evidence for dark energy, and together they really opened this era of precision cosmology. Subsequently, a WMAP satellite, which is Wilkinson Microwave Anisotropy Probe, was launched, and its purpose was to do this measurement even more precisely. And today, the best results we have come from analysis of the data from WMAP. So here is how this works. If you were to take an image of the cosmic microwave background, it'll be pretty uniform. And so you have to turn the contrast knob by a factor of 1,000. And then you see that there is a dipole due to the motion of the Milky Way relative to the microwave background. If we then subtract that dipole and then turn the knob to even higher contrast, to 1,000,000, then we'll see fluctuations in the sky, a lot of them associated with the Milky Way galaxy, the foreground emission from synchrotron and dust and so on. And after careful modeling, which is very difficult and very delicate, emission from the galaxy has to be removed. And what's left is a pattern of density fluctuation